Hello, everybody, and welcome to the fourth lecture. Changed format. There were some complaints that it wasn't so easy to hear me before, so we've changed this format. Let me know what you think. Okay, in part one, recall that last week, or in the last lecture, we were dealing with nilpotent algebras, special type of algebra that was somehow at the other extreme to simple. It had lots of ideas. This week we're going to make a generalization of nilpotent to something called solvable. Okay, so that's solvable is going to be the focus of this week's lectures. And what you'll see is it will generalizes the definition of nilpotent, and a lot of the results that were there for nilpotent algebras will generalize to this context, to this setting. Okay, so before we do that, though, we've just some unfinished business from last week. We had proved Engel's first theorem. Remember, it spoke about a representation of an algebra such that all of the elements, row of X in the representation, were all nilpotent. What we're going to do now is with Engel's second theorem, which is a consequence of this. Okay. Sorry, Engel's second theorem, which is a consequence of Engel's first theorem. So a Lie algebra, L, is nilpotent if and only if the adjoint action of the Lie of X for all elements X and L, if this is nilpotent. So here you really see where the name nilpotent comes from. It is equivalent to the nilpotency of the operators coming from the adjoint representation. Okay, which is nice. So let's look at the proof. So as we saw when we first introduced nilpotent, if you go back to the earlier lectures, you'll see that L to the n, if we take the series, defining series of a nilpotent algebra, if this is equal to 0, then we must have that the adjoint is equal to 0 for all X. Okay, that was just an easy consequence of the definition. On the other hand, let's now try to go, this is an if and only if, so let's try to go in the other direction. If we assume that add X is nilpotent for every X and L, then applying the first of Engel's theorem, as established in the last lecture, to the adjoint representation, because the adjoint representation is a representation, hence we can apply Engel's first theorem, which was a more general theorem about any representation, but in particular applies to the adjoint. Then we'll find a filtration by subspaces. Remember that this was one of the consequences in Engel's first theorem, that we had the series of subspaces such that L acted to move you along the chain of inclusions. Such that, here, this is what I mean, moving along the chain of inclusions, such that it brings the subspace V sub k into V sub k minus 1. Then that means, what does that mean? I mean, if we recall the definition of the adjoint is defined in terms of the commutator bracket. So it means precisely this. Okay. It means that, and sorry, there's a typo here, this should be k minus 1. Okay, I think that's clear. But that means that if we apply L again and again and again, we keep on moving down this chain of subspaces, which means that eventually, at some point, we're going to get to 0. And which is to say that L is nilpotent. Okay. So hopefully that's Engel's second theorem, derived as a consequence of the first. Taking the results in Engel's first theorem and applying them to the representation, the adjoint representation. So now we're going to move on to solvable Lie algebras, this generalization of nilpotency. So for I and J, two ideals of a Lie algebra L, their commutator is again, an ideal. So we proved a special case of this last week when we assumed that I was equal to L, the Lie algebra itself. And now we're going to do a generalization of this proof. This more general lemma will be needed when we're looking at in the next slide about the basic properties of solvable Lie algebras. So if I have an X in L, I have an A in I, and I have a B in J. Sorry, that should be a small b. Then it follows from the Jacobi identity. We're trying to, so we've got this commutator here, okay? If this guy is an ideal by definition if for every A and B, the commutator will actually lie inside in this guy here, okay? So we have to check that this lives inside here. That's precisely what the definition of an ideal says. How do we do it? Well, we can re-express this using the Jacobi identity as x with A and B plus A by xb. But we see that the two of these things are actually contained. The first guy, because we've managed to rearrange, we've been able to rearrange the brackets using the Jacobi identity. This is going to land inside in I, this part here. And then this is in J by assumption. So that means that this product here actually lies inside an IJ. And in the second one, it's the same argument. We see here that because J is an ideal, X and B, they're going to lie inside in J. And again, A is in I by assumption, so the product lies inside here. Thus, we see that this is again an ideal. Okay, so this generalizes the proof that we had last week. And it's extremely useful. Okay, so with that lemma in hand, we can move on and define a solvable Lie algebra. So that L be a finite dimensional Lie algebra. The derived series of ideals is given by L0 is defined to be 1. Sorry, L0 is defined to be L itself. And then L to the n, it's defined recursively. And what you do is, for each element in the series, you take the previous element and take its commutator, or take its Lie bracket. Okay, so remember, compare this now with the definition of a nilpotent ideal. So for a nilpotent ideal, the first entry here was the whole Lie algebra. Okay, there was just remove this guy here, and you would get the definition of nilpotency, of the series for nilpotency, the central series. Here we're taking something smaller. Okay, but just like for nilpotent, it's going to be solvable if this eventually gets to 0. If you keep on repeating this process, you eventually get to 0. So you can see, well, let's take the definition. Let's try to take the definition apart and look at some of the first consequences so we can make sense of what's going on. So note that by the previous lemma, each ln is an ideal. Because this guy is an, if we, I mean, again, this is an inductive argument. So if this is an ideal, then the commutator is going to be an ideal, and so on and so on and so forth. And of course, the starting point in the inductive argument is L itself, and that's clearly an ideal. So we get this, the derived series is actually a series of ideals. What's an example? Well, the easiest example is something which is abelian, just like in the nilpotent case. Because then, of course, you take the commutator bracket, the first element in the series to be L, and the second one, once you get to L1, then it's already 0, because the commutator of everything with any two elements is 0, so the whole thing will be 0. So we see that just like nilpotency, abelian is a trivial example. And what I said before, solvable actually generalizes nilpotent. Why is this the case? Well, it's just an easy inclusion. So we see what the definition of L to the I plus 1 is equal to I and I, the Lie bracket of these two. But this is contained, this is because Li is contained inside an L, by construction, then the Lie bracket of these two spaces is contained inside an Li. But this is precisely L to the I plus 1, and given in the definition of nilpotency. So we see that if this guy eventually goes to 0, if this eventually goes to 0, then because this is contained inside in it, it's something smaller. So if this is 0, then the smaller thing certainly has to be 0, which means that solvable implies, sorry, that nilpotent implies solvable. Not, of course, the other way around. Nilpotency is a stronger condition. It's so we can now really start to understand nilpotency as sort of a special case of solvable. But as we'll see, it's useful to have both notions. Wait, let me check. I think I'm sorry. So now, let's consider L by L. If the first ideal in the series, note that for the nilpotent and solvable, these are the same, the first element in the series. It's only after this that they actually change. Okay. Because if we go back up here, we see that when it's L0 and L0, this is L and L. So L1 is the same. It's only going to be in the second that they actually change. But if we take this guy here, and it's nilpotent, then we claim that this actually implies that L is solvable. Okay. Why? Well, nilpotency of L implies that L to the n plus 1 in brackets is equal to L prime to the n, which is contained in L to the n, for some n greater than 0. Thus, we see that it's actually solvable. Okay. So somehow this is maybe one way of looking at it. It's almost like pushing the solvability is almost a little bit like pushing the nilpotency just one step beyond in the series. It's, yeah. Okay. In fact, what the goal of this lecture, where we the final point or the final result of this lecture, and not to spoil things for you, is going to show that this is actually an if and only if condition. That L is solvable if and only if L prime is nilpotent. But that's something that's going to, we're going to have to do some more work to get to this point. Okay. So let L be a Lie algebra. It's the first lemma about solvable ideals. So if I is an ideal, then L is solvable if and only if I and L over I are solvable. So it's a way to, you can do it almost like as a technique for checking if something is solvable. All you need to do is pick one ideal, look and see if that ideal is solvable, and if the quotient by that ideal is also solvable. If they are, then you know that your Lie algebra is solvable. If they're not, then you know it's not solvable. Moreover, sorry, this is a typo here as well. This should be a uppercase I. So if I are solvable, they're two solvable ideals, then by taking their sum, just to say just the linear span of all of the elements in I plus j, then you know that that this sum of the two is actually solvable as well. Okay. So let's prove that. Let us assume that our Lie algebra is solvable. Let's start off in that direction. Okay. We need to prove it from both directions. It's an if and only if. So let's start off under the assumption that it's solvable and show them that for any ideal I, this implies that I is solvable and that the quotient space L over I is solvable. All right. In particular, let's know first, because L to the n is 0, that would mean that for any subset, such as I, contained inside there, when we take the derived series of this, then that also has to be 0 because it's contained inside something that's 0. Clear. Hence, we see that L is solvable. Okay, so that this solvable of L implies solvability of I is actually pretty easy. To show that the quotient space is solvable takes a little bit more work. So let pi be the canonical projection. Okay, you just take an element and you map it to its coset inside this quotient space, and let us prove by induction that pi operates on the kth term in the derived series to give you the kth term in the derived series of the quotient. Okay. This is what you would expect should happen. In fact, it does, but we need to prove it. So, as many times before, we're going to prove it using induction. So it's clear that it works for, I hope for k is equal to 0 for the first term. So that our starting point is clear. We just need to assume now that it works for k, and show that this implies that it works for k plus 1. So let's take pi of L to the k plus 1. What is this? Well, let's write out what this is. It's going to be, you take the previous term in the derived series, L to the k and L to the k, and you take their Lie bracket. That's what it is. Now you operate by pi, and if you think about this for a second, you'll see that it's true. I mean, it's clear that in fact this pi here is going to be a Lie algebra homomorphism, just basically by definition. Then we now know, well, now that we've got to the point where we're looking at pi of L to the k, we're now able to take the inductive assumption, the inductive hypothesis, and apply it, which is to say that this is equal to this. And of course, the same thing, this is equal to this. But what is this, the Lie bracket of these two spaces? Well, that's precisely this, by definition. And that's it. So we've shown that if it holds for k plus 1, then it holds in general. And then applying, and hence by induction, it holds for all k. So that's good. We've now proved, this. Okay, so let's use this. So in particular, if we take the nth series, and oh, there's an extra bracket here, again, my apologies. If we take this guy here, L to the n, this is 0, because we're assuming it's solvable, so there does exist such an n, so that eventually goes to 0. Well, this is 0, so pi of this will have to be equal to 0. Okay, this is clear. But that means that because now we know that these two things are equal, that means that this is 0, which means that this guy here is solvable. Okay, so that's it. We've now gone in one direction. We've shown that solvability implies that any ideal I is solvable, and the quotient of L by the ideal is also solvable. Now let's go in the other direction. I guess the direction that solvability implies solvability of ideals and quotients, maybe that's what you'd expect. Maybe it's less obvious that going in the other direction actually works, that you can pick any ideal, and if it's solvable and the quotient is solvable, then the whole thing is solvable. Well, it's actually true. So let's assume that I is solvable and that the quotient is solvable. Again, the n and the m don't need to be the same. I mean, of course, you can just take the maximum, but it may be that this thing terminates sooner or later than this, but it's not so important. So we know that there's such an n and an m exist for some positive integer. Then from this, we see that operating on pi of L to the n, by the general result that we proved by induction in the last slide, we see then that it's equal to this, which is equal to 0. What does that mean? We'll just look at the definition of the quotient space. If something is 0 in the quotient space, that means that it must have been contained in the ideal. Okay? By definition of what the quotient is. This in turn implies that L to the n plus m is equal to 0. Why? Because, well, L to the n lives inside in this here, this ideal I. If we know that I to the m is equal to 0. So if we keep on applying the process, I mean, applying it to this space, it's going to be the same. I mean, when you restrict it down to the subspace, of course, it's just the same thing. So yeah, that means that then taking L to the n plus m is going to give us 0. Okay, and hence, particular L itself is solvable, showing that the two conditions are actually equivalent. So it's a neat trick. Step one, just to recap, to summarize, step one is looking at the image of L inside in the quotient, or L to the n inside in the quotient, and realizing that this has to be 0 because the nth term in the derived series of the quotient space is 0 because it's solvable. Hence, of course, this thing has to be 0. That means, what does it mean for it to be 0? It means that it's contained inside in the ideal. The fact that it's quotient, that it's 0 in the quotient space, means that it was contained inside in the ideal in the first place. And then we use the fact, step 2, then we use the fact that the ideal itself is solvable, which means that its derived series eventually terminates. But if the derived series of this eventually terminates, then we know that the n plus n in the derived series of L itself actually terminates. So two-step process, quite nice. And showing us that the two conditions are equivalent. So let's now use this to show that the span, the direct, or the sum, not the direct sum, the sum of two ideals is solvable. Just to say the span of all of their elements, linear span of all of their elements. So first of all, let's take the elementary identity. If we take I plus j quotiented by I, this is isomorphic to j over I plus j. Okay, this is just a very basic linear algebra argument. I'm looking at it quickly. We see that, of course, this is going to be 0 because we're quotienting by I, which means that we're just left with j. But it's only going to be the elements inside in j itself. It's only going to be the elements that are in I that actually affect the quotient j. So it's going to be the intersection. So if that's not clear to you, it's a good thing to sit down and write write down maps going in either direction and show that they're inverse to each other. Set up a linear isomorphism between these two spaces. Okay, go over here should be the identity in the same way around, the other way around. And then convince yourself that this is actually an isomorphism of Lie algebras. Okay, there's really nothing there, but just take some time to get it straight in your head is a good idea. But from this guy here is actually easier to deal with in some sense. What does it mean it's easier to deal with? Well, this presentation, it follows from one, that if j is solvable, then so is the quotient. Okay. Remember, in one we showed that if something is solvable, then any ideal and any quotient, the quotient space corresponding to that ideal are solvable. So, so then j is solvable. Remember, the intersection of two ideals is an ideal. So j is solvable. The intersection of I and j is, of course, contained inside, and it's a sub-ideal of j. Hence, it must be solvable, and hence the quotient is solvable, which is what we're saying here. Therefore, j is solvable. And hence, since I is solvable by assumption, okay, so this is solvable, this is an isomorphism of Lie algebra, so then this is solvable. But we're assuming that the ideal I is solvable. So we know that I and the quotient space is solvable, hence going the other direction, using the other direction in part one, we can conclude that I plus j is actually solvable. And there we are. So when we have two ideals and we take their sum, not the direct sum, their sum, then they are solvable. Okay. So that's a great way of constructing solvable ideals from solvable ideals, just taking their sum. An extremely important example of this is given in the next corollary. So we see that the radical of L, this is a definition. What do? We take all solvable ideals, all ideals in L which are solvable. Sorry, I can't highlight this. All ideals I and j which are solvable, and we take the sum. Then this has to be solvable by the previous lemma. Because if we take two things, they're solvable. That gives us a new ideal. Then we add the next guy and the next guy and so on and so on and so on. And we're going to end up with something that's solvable. And this is going to be the maximal solvable ideal of J. Okay, it's clearly maximal because if there was something else that contained it, then that would have had to have been in the sum in the first place, which means that it's already contained inside there. So yeah, of course that can't happen. So it has to be maximal. And we call this maximal solvable ideal of J, we call it the radical. And it's a very important, remember that there's no assumption here that L is actually solvable. This is a general Lie algebra. L is a general Lie algebra. There's no assumption at all. But it means then that we've always got this like maximal solvable ideal inside in J. Sorry, in L. And this is really, really important part of the structure of a general Lie algebra, the radical. And it exists for any Lie algebra L. Okay. Now, let's make another quick observation. If we take this filtration of ideals, this is the derived series, okay? You see that everything is contained, one term is contained in the next and so on and so on and so forth. If we take a quotient of one term by the next term, then this is abelian. That's the claim. Why is it abelian? Well, this is actually a fact for any Lie algebra. If we take a Lie algebra and if we quotient by the first term in the derived series, it's L and L, then it has to be abelian. Why is this the case? Well, it's the case because if you take then the Lie bracket of any two elements in L, then of course it will live inside here. It will live inside in the quotient. That means that it's going to be its coset is going to be contained inside in its coset is the zero coset. This element lives inside in the coset containing zero. Hence it's zero. Hence the Lie algebra itself is abelian. But this is precisely what we're doing here in this series, because when we go from one to the next, L plus L to the k plus 1 is the Lie bracket of LK and LK. Hence a special case of this general result. Hence it's abelian. So we have this filtration of things that are abelian inside there. Okay, this is an important point. Remember, you probably have seen something like this in group theory as well, where you're going to produce commutative groups by quotienting out. But anyway, that's not so important for us here. Okay. And now we're going to finish the first part of this lecture with the theorem by Lie. This is the generalization from nilpotent to solvable of Engel's theorem, Engel's first theorem. So good idea, and very important idea is to come and see how the two things, how one generalizes the other. So remember, solvable generalizes nilpotent. This theorem generalizes the result we had of Engel's. So we should see what things carry over directly or still true when we generalize from nilpotent to solvable, and which things aren't, or how they change, or what exactly is weakened. It's a very good way to get a feeling for the difference between the two things. Okay, just to sit down, open up the screen and put the two theorems side by side and compare and check which results carry over and which don't, so how the two things compare. So let L be a solvable Lie algebra over an here we're going to restrict to algebraically closed fields of characteristic 0. Okay. I guess in this course, almost always we're going to be really thinking about Lie algebras over the real numbers of the complex. And in this case in particular, we're going to be thinking about them in complex because it needs to be algebraically closed. And let rho be a non-zero representation of L. Okay. Now remember in Engel's theorem, it said that there was always going to be an element V, small v inside and big V in the representation that was going to be killed by every element of the Lie algebra, or more precisely, rho of X for every element in the Lie algebra. That's not what happens here. There's a generalization. It generalizes to an eigenvector. Sorry, this is a typo here. It's not eigenvalue, it's eigenvector. So it generalizes to an eigenvector. In Engel's, it was going to be an eigenvector where the eigenvalue was 0. Okay, an element in the kernel. But here, it can be, it generalizes up to an eigenvector. Of course, the eigenvectors don't need to be the same for every element of the Lie algebra. It just needs to be a common eigenvector for all elements of rho of X. Okay. So we've from here, solvable, nilpotent generalizing to solvable goes from eigenvector with eigenvalue 0 to general eigenvector. All right. Next, remember that we could always choose a basis of V such that for every element rho of X, it was upper triangular in this basis. Here, strictly upper triangular in Engel's theorem. For nilpotent, it was strictly upper triangular. Here, we're generalizing from strictly upper triangular to upper triangular. So that's a very good way to think about the generalization from nilpotent to solvable, that we're going from upper triangular, strictly upper triangular matrices to upper triangular matrices. It's a good idea to keep in your mind. And these tricks or these examples, these analogies are a very good way to learn. Because of course you're all very familiar, you know what the difference, immediately you see the difference between how upper triangular is a generalization of strictly upper triangular. To see to get a feeling for how solvable generalizes nilpotent is more difficult, but so this idea is very, very useful, that we're somehow generalizing from strictly upper triangular to upper triangular. And finally, we see that there exists a chain of sub-representations such that the dimension is equal to 1. Remember, we had this sequence as well for nilpotent, but we had a stronger condition whereby the Lie algebra acting on it would move you along. Here, this is not the case, but we get this chain of sub-representations. And we have that the dimension of the quotient of one by the other is equal to 1. Okay. So this in particular also works, if you recall the sequence that we had in nilpotent, the dimension here of the quotient spaces is actually equal to 1. We didn't prove it for nilpotent, we're going to prove it for solvable, and then of course that implies it for nilpotent. And yeah, that's it. So we're not going to prove Lie's theorem in this part of the lecture. It would be the proof of the second. It would be the second half of the lecture. We will also prove what I referred to earlier on, that a Lie algebra L is is solvable if the first term in the derived series is nilpotent. In fact, and again, that's another way to see, to think about how solvability generalizes nilpotency. But anyway, we'll see that in the next half of the lecture. Okay, thank you for your attention.